In this chapter, you will learn the conversion of motion equations derived for spring mass damper system into a Python model. The procedure for modeling is similar to that of longitudinal dynamics model of the car. The difference lies in the inputs, outputs, and the system model. Above main, we have the step input function, which I copied here right now, and the system model. Since we already know what a step input function is, I skip that explanation and go directly to the system model explanation. System model function smd underscore model gets the following inputs. X, the system states 2D array, T is the time step, M, D and K are input constant values, the mass, damping coefficient and the spring stiffness used in the equations of motion. Fin is the force input. The 2D array X is extracted into two variables. Now we define the spring force Fs is equal to K into X, stiffness into displacement, and damper force Fd is equal to D into X dot, damping coefficient into velocity. From the equations of motion, we know that X double dot is equal to 1 by M into external input force Fin minus spring force minus damper force. We return the values X dot and X dot dot. Similar to the previous example, below main we have the commands to run the simulation. So here we declare the constants mass is equal to 100 kilograms, K stiffness factor is equal to 50 newtons per meter, damping coefficient D is equal to 50 newton seconds per meter. We give F naught, the input force default, is equal to 50. In case if we need to use the initial force, we can take this value. As usual, we create the rest of the simulation setup with start time, end time, step size, and calculate the number of steps. We also create the time span array and the boolean for controls on and off. Then we define the input array u of t. In our case, it is the force input of step function. Force increases from 0 to 50 Newton during 4 to 5 seconds. A force array is created using the step input function, similar to the previous example. Theoretically, for 50 Newton force, the steady state value of displacement should be 1 meters. We could check it when we run the simulation. Collectors are created to store the calculated results and plot them. State variable is a 2D array, acceleration is 1D array, and error collector is again a 1D array. Next step is to program the simulation for loop. The odeint function receives the SMD model function, initial states, time step, and the inputs mass, damping coefficient, stiffness, and force in. Output of the odeint is stored in the result collector named state underscore var. Acceleration array stores the acceleration calculated from velocity and time. Print statements and plot commands are created after the simulation for loop. Now we can run the simulation. There are some errors in the program. Let's correct them first and then run the program again. Now the errors are corrected. Our program runs. As we theoretically calculated, the final displacement approaches close to 1 meters. If we look at the graph, force input varies from 0 to 50 newtons between 4 and 5 seconds. The displacement of the mass begins to vary at 4 seconds and it reaches 1 meters at the steady state towards the end of the simulation. To have the closer look at the steady state value, we change the simulation end time to 100 seconds. So the simulation runs from 0 to 100 seconds now. In this updated graph, we can see that the displacement reaches 1 meter around 25 seconds. The corresponding velocity and acceleration are also plotted in the curve. In the next section, let us look at how to program a PID control to control the position of mass based on the force input to the system.